In the bustling world of urban logistics, every moment counts. Whether it's Careem groceries delivering your groceries to your door, or Careem food bringing your favorite meal, precision is key. Behind the scenes, there is a web full of merchants, captains, and routes working tirelessly to ensure seamless deliveries. But how do we make the system smarter, faster, and more reliable? Careem is a one-stop platform for urban services. Two of these services are Careem Food and Careem Groceries. Two of these services are Careem Food and Careem Groceries. Two different challenges are faced when we're trying to optimize the efficiency of these services. And our aim is to find them innovative solutions. This ambitious project wouldn't have been possible without the collaborative effort of our dedicated team. Ladies and gentlemen, please allow us to introduce ourselves. Kirola Zakaria, Muhammad Azazi, Ahmed Badr, Lina Sirri, Nurhan Al-Atyar, and I, Nada Badawi.
Okay. So our first challenge focuses on Careem Quick, which is their grocery platform, where we aim to optimize captain replenishment through a smart allocation system. To better understand the problem, let me introduce two of the issues that Careem delivery model faces currently. Okay, so the first issue happens when orders are ready at the store, but there are no enough available captains to pick them up. And the second issue happens when orders are ready at the store and there is a captain assigned for them, but the captains get delayed on their way to pick up the order. So to better understand how these issues affect the delivery process, let's walk through the delivery process. First, once the customer places an order, it enters the system to a specific merchant, and then the merchant start doing two things. First, they start preparing the order, and they start assigning a captain. However, if there are no enough available captains in the system, the captain assignment will be delayed, which is the first issue. But once assigned, the captain will head from their location to the customer to pick up the order, and then finally deliver it to the customer. But the main challenge here is the first mile time, which is the time taken by the captain to travel from their location, once assigned, to the merchant location, which means that sometimes the preparation time is much smaller than the first mile time, which makes the order ready at the store, waiting for the captain to arrive and pick them up. So our aim in this project is to optimize the first mile time by basically pre-allocating captains at the merchants before the order is being made. So before the order is placed, the captain will be waiting at the merchant, waiting for the order to be placed. We're going to achieve this through a data-driven demand prediction model that decides when and where captains are needed the most. And through this, we're going to achieve an end-to-end optimization of the delivery process. And now I'm going to walk us through the methodology of our doing this. First, we started by analyzing 3 months of historical data of Careem to understand the patterns in demand and delivery. And then we transform this data and we clean it to make sure it's ready for modeling. And then we use time series forecasting models to predict how many orders are going to be made per 10-minute intervals during the day. And then we compare these forecasts with actual data. And finally, we simulate this to the real-world scenario system to measure the overall efficiency optimized. And now, Krolos will walk us through the details of the methodology.
So our goal was to predict the demand per 10 minutes interval. So we first tried to find a pattern within the hour. As you can see here, there is no any pattern. Each interval in the hour exhibits the same behavior. So we try to do it on an hourly basis. So as you can see here, in day 5 and 6, they have similar pattern, but in day from 0 to 4, it exhibits a different pattern. So we try to investigate this more. Uh, Here is the histogram of the average order throughout the whole week. And when we divide it by weekdays and weekends, it gives us very different distributions that can really benefit the prediction power of the model. Next. So we came up with this feature engineering. These two features is weekend and is rush hour, gives the model the adequate information to predict the number of orders along with the trend and seasonality. Next. So what's our journey with the demand prediction? First, we started with ARIMA model. ARIMA is a basic machine learning model for time series forecasting, but it was not enough for the complex seasonality in the data we have. So we came up with XGBoost. XGBoost is a decision tree based approach. It increases the performance, but it was not enough yet. So we moved to Facebook Profit. Facebook Profit is another time series forecasting model that depends on the trend, seasonality, uh, holidays, and an error margin. It was good performance, but we tried to optimize more, so we went to Neural Profit. Neural Profit is based on Facebook Profit, but it has the auto regression part, which is a deep learning part. Next. In neural profit, we had four approaches. First, the basic approach. Second, the recursive approach. The basic approach is like inference on one time for the whole day. In the recursive approach, we divided the day into 24 hours, and we predicted each hour recursively. And in the two ensemble model, we tried the bagging and the boosting. The bagging is basically two models in parallel, and the boosting is two sequential models that are trying to learn from the mistakes of the previous model. So here is a snapshot of the results that will be viewed by Careem merchant with a prediction interval for the merchant to have the flexibility to choose the right number of orders based on the day traffic. And here is our business impact per approach. And as we can see, the recursive approach have a consistent performance across all merchants and slightly better in most of them. And here are our business impact. So the red line here exhibits the average delivery time, and the green line is the average delivery time after our improvement based on our simulation. And we will move to the second challenge of our problem.
And now for our second challenge. When it comes to food delivery, efficiency is optimal. And what if instead we deliver each order on its own? We can pool multiple orders and deliver them on an optimized route. This is where the challenge comes in. Estimating ETAs for pool deliveries. Now imagine you're ordering food on the Careem app. You add to cart and click place order. What happens when you do that? Behind the scenes, your data goes through 3 stages. The first stage is the routing engine, which operates like Google Maps, showing the driver the perfect route to go from where he receives the order to the merchant to you. The second is a pooled route optimizer, which looks for other orders in the area that can be pooled with yours to minimize the driving distance and maximize his efficiency. And the third is an estimated time of arrival calculator to show you how many minutes it would take for the order to arrive at your door. In order to do that, Careem gave us 2 datasets. A trips dataset, which had general information about each trip, like distance, time, and delivery time, as long as wait times along the trip, and captain and merchant assignment. The other dataset is pings, which has trajectories for each trips at 5-second intervals. And in each point, you can see where the driver is, his location, and of course, his time and status. We had 2 months of data from Careem, Jan and Feb of 2024, for Amma and Jordan. But why are we doing this for Careem? Don't they have their own things? Of course. But they still want to maximize their efficiency, minimize the driving time, cost, and delivery time. And with that, we start with our first component.
So the first component is a routing engine. Routing has both technical goals and business goals. The technical goals of routing involve finding the optimal path from the merchant to the customer while taking into account traffic. The business goals involve cost savings by basically using an open source and free routing engine such as Valhalla or OSRM and also circumventing the usage of APIs such as Google Maps here and TomTom to obtain traffic information and ETAs. So including traffic within Valhalla has proven to be much simpler than including traffic within the open source routing machine. So we've opted for Valhalla as our open source routing engine. Also, traffic within Valhalla can be of two categories: live traffic information or historical traffic information. Historical traffic information is much simpler and more cost effective to include than live traffic information, because live traffic information relies on APIs, and we're trying to circumvent the usage of APIs. So the first phase in including traffic within Valhalla involved fetching the OSM data of Jordan from GeoFabric and then passing it to the Osmium tool to extract Amman's OSM data using its bounding box coordinates. Next slide. We used Amman's OSM data and passed it to the Valhalla tile builder, which also takes in the configuration file generated by the Valhalla configuration builder to generate preliminary tiles without any traffic information. The tiles are then passed to the Valhalla waste to edges mapper, which generates a mapping of OSM IDs to Valhalla graph IDs, and this is a one-to-many mapping. This text file, which contains the mapping, is then passed to the integral component of our whole process, which is the traffic CSV writer. It takes in Careem's traffic information, basically OSM IDs are mapped to traffic information, and these are passed to the Valhalla, the traffic CSV writer, which writes the CSVs into the traffic folder within the build folder of Valhalla. These CSVs are then written to the routing graph of Valhalla using the Valhalla add predicted traffic tool, which also makes use of the configuration file to locate the tiles directory. Behind the scenes, we obtain the traffic speeds from Careem's dataset without using any APIs. So this is a very cost-efficient way. It actually costs nothing at all. And we use these traffic speeds, map them to the respective coordinates of the trips. Then we remove the coordinates and replace them with the respective OSM IDs obtained from the service of Valhalla itself. Next slide. We also automated this process by creating a watchdog which monitors the traffic CSVs folder. Once the 18 CSVs have been modified, you basically write the traffic information onto the routing graph using the Valhalla add predicted traffic tool. Then we monitor the service. If the service is running, we restart it so that it can detect the changes in the traffic information on the routing graph. If it's not running, it's simply started. After determining the optimal route for the whole trip, we basically need to pool the orders from the merchants to the customers.
Now, I want you to imagine with me that I am here in AUC, which I am, and you are across the street. And when that is happening, and we order both of us orders from the Careem app, instead of sending 2 individual captains to each of us, we want to send as the same captain for us. But why do that? We do that because we want to reduce total vehicle distance kilometers traveled, and we want to decrease environmental impact, and we want to lower operational costs. But how would we think about doing that? We think about doing that in a very simple way. We receive new requests, we want to store those new requests somehow, and then we want to do some basic checks to think about whether it's even feasible to do pooling in the first place, and then we do the route planning, and then we recheck. If it passes, we go on pool. If it does, it doesn't, we go solo. And that is exactly the very first thing we do. We start by taking up the trips and putting them into a spatial indexing grid-based system based on the coordinates, where each time we want to try and search for a trip, we search for the trip in the grid, and the trips around it will be the trips that is close to it when it comes to the coordinates, so that we can search fast and efficiently, which resulted in an end result of the running system in 2 minutes for each trip for a whole day. And now, the second thing is that we want to determine the basic feasibility of pooling, and we do that by checking the max pickup distance between 2 trips. We want to check the max time window, that both trips were made in similar time, and we check the distance compatibility, that both trips are going in similar directions. Finally, we generate a priority score in order to check which trips we want to try to pool together first. And we do that by checking a distance score. Longer trips will have higher probability of pooling, and a demand score. Areas with more historical requests will have more likely to be pooled, and time score, peak hours, will get higher priority. And finally, efficiency score based on the route directness. The last thing is that after we do the trip pooling, we generate a matching quality score for future reference in order to check the distance efficiency, time compatibility, pickup convenience, and demand patterns for those trips. And this is the full architecture of our pooling system, starting from the input sources to the core processing and the output analysis. Now, I want you to look at those two trips that were deemed not feasible to pool in Careem's dataset, but actually, after putting them into our routing engine and pooling system, we have found that there is an optimal route that is optimized for those two orders. But what about a larger scale? When running onto one of the 3 days in Careem's dataset that we have, we found that from 4.7 average daily requests and trips, we have found that there is an average pooling rate of 48.77% in each day. And that is a great success over what Careem has. Finally, after pooling the trips, what about the time that will show to you on your application when you make an order?
So for ETA, we went with a 3-model approach. The reason we went with this approach is because of some problems we found in the data that we're going to highlight later, and we found this to be the best solution to overcome these problems. Our first model deals with driving time, when the driver is on the road from when he receives your order to when he gets to the merchant, and then leaving the merchant and going to the customer. And the second model deals with the wait time at merchant, where the driver is waiting for the order to be ready. And the third takes the outputs of both models, giving us the total and final ETA that is presented to the customer. So our first model is a random forest regressor, which is a great machine learning model for time prediction due to its ability to handle noisy data and geographical variability. It takes features such as time and date, some driver information, pickup and drop-off zones, giving us the delivery time as the label. Our second model is XGBoost, which is another machine learning model for time prediction, and it worked really well with the complex patterns that we had in our data. It takes more merchant-related information, such as location, order frequency, and food preparation time, giving us the wait time at merchant. And for our last model, it takes the predictions of both XGBoost and RFR, giving us the total and final ETA. In order to show you some of the problems we faced in the data, we decided to model a trip that we took from Careem's data. So as you can see here, the driver, which is the yellow dot, is not stationary at the merchant during his waiting period of 20 minutes. He's moving around the merchant. And because of that, we had discrepancies identifying the wait times and the driving times. Another problem we had is the low precision of data, where in our data we had coordinates with only 3 decimal places versus the standard, which is 6. So between each coordinate and its neighbor, we had 150 meters. And due to that, that led to discrepancies in segmenting the trips, as well as you can see, when the driver starts moving towards the customer, he's moving sporadically and with no clear route. That is due to the precision, as well as having missing pings in the trajectories of the trips. And due to that, the accuracies of our model was not as high as we hoped, but we did our best to come up with solutions to overcome that and get as close as possible to the ETAs.
So due to the issues that we've just witnessed, we had to go for a segmentation technique. And that's basically to segment each trip into 3 different segments. And in fact, actually, that led us to have nearly 1.5 times more of the road trajectories than we originally had in our data. And that all was to only reduce the prediction uncertainties. Something else that we had to do in order to enhance our model was to build a good relationship between the geospatial data and the predicted ETA. So we had to go for a clustering technique, and that's just to capture any regional information that should be fed into the model. So which clustering algorithm did we choose? We actually went for, in order to determine that, we had to overlay the coordinates to see its distribution over Amman's map. And we found out, as you can see on the screen here, that it actually follows a grid-like structure. And that guided us into thinking of a cluster algorithm that would be actually grid-based. We chose the statistical information grid, aka STING, and that's because it got us the best results once it's integrated into RFR. And each or any 2 coordinates that are actually belonging to the same grid cell will be labeled as a single cluster, and every trip will have a start cluster and an end cluster that would be attributed to and fed into the model. So after some model training and testing, we actually found out that the first model is getting us an accuracy of 75% or a marginal error of 2.48 minutes. As also the second model that predicts the merchant wait time gave us a marginal error of 3.1 minutes. The third model that predicts the overall ETA was away with nearly 4.27 minutes from the actual trip time. So what do actually these values mean? After having a look at these figures, we actually found out that we actually did it. We did satisfy Careem's criteria once we actually contacted them that they had the business requirement of having a marginal or a buffer of 5 minutes between the actual delivery time and the estimated arrival time that was shown on the user's screen. And also, that we satisfied this criteria, although we had an issue of lack of traffic conditions and all of the previous problems that we have discussed earlier. We wanted to take this a step further by removing the quality of data as a factor and compare this, benchmark it against Valhalla's output. We found out that there's only a difference of nearly 2.93 minutes between the output that Valhalla got us and what our solution got us. And now that's all what happens behind the scenes from the moment you place your order until you actually receive the ETA on your screen.
And now, last but not least, we want to talk about the achievements and our empowerment outcomes. We here want to say that we have successfully managed to achieve 2 empowerment outcomes. The very first is product deployment. We are in talks with Careem in deploying the solutions that we have made for both challenges, problem 1 and problem 2. And secondly, we are writing 2 papers that are addressing one of each of the first the challenge we did and one for the second challenge, as you can see here. And both of them wouldn't have been, and all of this wouldn't have been made successful without the continuous support and mentorship of our supervisors, Dr. Amr Mugi and Dr. Nouri Sar, and our industrial supervisors, Mr. Salim Turki. Thank you very much. This was Group 1.